So, we talked of volume currents and surface currents, and now it is turn of linear currents, and that is the most familiar current that we use in usual circuits, because there are wires through which the current goes and those wires define a line. So, essentially everything is volume, but if that thickness is much smaller than the length and then the motion is along the length, there is no motion sideways, then this is a good approximation, where we say you have a line and in that line you have charges and those charges are moving. So, suppose you have a linear charge density on the line, the line on which this current is there. So, you have lambda, we write it lambda, and what is this? If you take a length dl, suppose you take a length dl, then the charge contained in dl, if this is your dq, then this dq dl is known as lambda. This is your linear charge density. So, it is the length. So, per unit length, charge per unit length, take a length dl, see how much is charge, divide by dl. So, that is charge per unit length, and that is known as linear charge density. So, if you have this linear charge density lambda, which may or may not be same along the line, maybe here there is another lambda, here there is another lambda, here there is another lambda, but whatever. So, if the velocity is v, here the charge density, linear charge density is lambda and the velocity is v. So, you can work out in a similar fashion what will be the current, how much charge will cross this section, this point here, how much charge will go from left to right through this point. So, once again the same story, if you consider this point and then you take a length v times dt, this length, how much is charge here, that is lambda into v into dt, and in time dt this whole charge will cross this point, because in time dt everything travels v dt. So, this charge will reach here, and therefore, all this charge in this length that must have crossed here. So, that is the charge dq which is crossing through this point in time dt, and how much is that? That is lambda times v dt, and therefore, the current dq dt is just lambda times v. So, if I collect all three, we defined volume current density J, and that was rho times V, where rho was the volume charge density. Then we defined K, surface charge, surface current density, which was sigma times V, and then we define this current, which is lambda times V. Okay, we do not define linear current density because it is crossing through just one point. So, I cannot divide by the size of that point. Here, when we defined this volume current density, we had a cross section. We have a cross section, we had an area, and then we asked how much is the current going through this area, and then we divided by delta A, current going through per unit area. So, that is how that current density is defined in case of volume. Then surface current density, here the things were going on a surface, but then we took a length dl and asked how much is the charge crossing this length dl per unit time, and then we said okay, if this is the charge crossing through this line, then we divide by that line and then it becomes per unit length, and therefore we define this K, current density, surface current density, which is current through this line divided by this line. But now here you only have a point, so I cannot divide by anything. How much charge is going from this side to that side per unit time, that is the current, that is it. Therefore, we do not define any linear current density, it is current itself through that point. Also, I will not put a vector here. You have a vector here, you have a vector here, but I have not put a vector here, because since it is current and current is a scalar quantity, we should not put this arrow here, although DJ Griffith puts an arrow here because current has a direction to show that direction. But then once you put that arrow, that means you are committing that it is vector, which it is not. So, these are the relations. Then we also talked of current elements. If we have current in a larger region, then point by point we can ask how much is the current here, how much is the current here. So, current elements we divide it in different elements. So, we have J d tau is the elementary volume d tau, and in that volume how much is the current. So, that is this J d tau is the current element in case of volume current. Then K dA that will be the current element in case of surface current, and this IDL that will be the current element for this linear current. So, we will be using these things in calculating magnetic fields. You will have some kind of current distribution, and then we have to take elements, small elements of that volume or that surface or that line, and then from each element we have to calculate magnetic field. Therefore, this is necessary. Okay. Now, we come to another equation which we call equation of continuity, for charges. This equation of continuity is essentially the statement of conservation of charge. Charges are not created and charges are not destroyed. Charged particles can be created, charged particles can be destroyed, but charge cannot be created, charge cannot be destroyed. So, that fact is represented by this equation of continuity in case of currents. So, essentially if we have some volume, suppose there is a volume, and then there are charges and they are moving in different, maybe different velocities in different directions, crossing the surface of this volume from here, from here, from here, from here, and so on. So, this is the situation, and then we define charge Q, charge at certain time, at an instant t, certain time t, that let us say this is a charge Q. So, Q is the charge contained in this volume at time t, and then we have currents at different places, we have currents. So, from here maybe the charges are going this way. So, you have a current from here. So, on the surface you take a small area element dA. Remember, we are working on a 2-dimensional board and we are talking of 3 dimensions. So, the geometry will not, this geometry itself will not reflect the situation very well. So, you have to make an imagination. So, you have a surface, and on that surface you are taking some kind of a small area dA. So, the surface is not only this line, the surface is everywhere. Suppose this is the kind of volume, then this whole thing is surface, and this dA can be here, can be here, can be here, can be here. That is why I am showing it here. So, how much is the current going through this dA? How much is the charge crossing this dA from inside to outside? So, if I call that di, what is di? Di is the current or the charge crossing per unit time, that makes it current. Through this particular dA, that we have chosen on the surface of this volume. So, how much is that di? That di will be J current density, volume current density, and dot product with dA vector. What is dA vector? The magnitude of dA vector is the surface area itself, and the direction of this dA is perpendicular to that surface and going in the outward direction. Since it is a volume and we are talking of surface of a volume, therefore, we can always talk inside the surface and outside the surface. So, the charge which is going from inside to outside, that is our current, and that is the direction of dA, perpendicular to this surface. Charge may not be going perpendicularly, but the dA vector will be perpendicular and the direction is in outward direction. So, this J dot dA is the current. So, in time dt, now let us say what happens. This is at time t, everything at time t, this is the time t, at time t this is the current density, and this is of course the small area that we have chosen. So, as time passes, the current density here can change. Maybe at this moment less number of charges or particles, electrons are crossing, but then after some time maybe more number of charges are crossing. So, this J can be dependent on time, this Q can be dependent on time. So, everything at time t. Now, what happens in next dt? Okay, so, this is all at time t. Now, in next dt, charge which has crossed this particular dA, how much charge has crossed this particular dA in that time interval dt. So, since this is current, the charge going out of the volume through dA in time dt, the charge which is going from inside the volume to outside in time dt, that much charge has gone out of this volume through this area dA. How much is that? That will be the current and then multiplied by time interval, that is the charge, that is how we define the current, and that will be this J times or dot product with dA and then into dt. Then integrate over the entire surface. That means, now we are adding this quantity, entire surface, the whole surface is now divided by such small dA, small dA. This whole surface is divided in such a fashion. From each dA we are calculating and then adding. What does this give? What does this give? This gives me the total charge that has gone out from this volume. So, charges will go only through the surface, all right, and then entire surface if I have already considered, then it will be the total charge which has gone out of this volume in time dt. So, the charge total charge going out of the volume, and everything in time dt, in that time interval dt, will be integration of this thing. This is your charge going through dA and then the entire surface. So, it is integration of j dot dA and then dt, and then we put a circle on this integration sign to tell that our surface is a closed surface, right, because it is enclosing a volume and therefore it is a closed surface. You also have open surfaces, but then open surfaces will not enclose any volume. So, this is a closed surface and therefore, we are putting this circle here. Now, if this is the total charge which has gone out, the total charge which was capital Q at time t, how much it is at time t plus dt. Okay. So, in time dt, what is the change in this capital Q? Remember, capital Q we have defined that charge at an instant t. Now, in time dt some charge has gone. So, at t plus dt the charge will be less than that. So, dq, when we say dq in calculus, it is always taken as the increment in q. So, since it is decreasing, dq itself is negative. So, minus dq is equal to this much charge has gone out. Integration j dot dA and then dt. That is the change in q. It becomes q2 q plus dq. Remember, q to q plus dq, this is a requirement of calculus. We always say that if at time t the function is y, at t plus dt the function is y plus dy. So, it is q plus dq, but then the charge is actually decreasing, this dq is itself negative. So, this is the magnitude which is actually decreasing. So, this is equal to this. Now, q itself can be written as, what is q? What is q? Take this dt here. What is this q? Q is rho d tau integrated over the entire volume. See, rho is the charge density, volume charge density. So, rho is charge per unit volume. So, if at this point your charge density is rho, it may not be uniform in this entire volume. At this particular point, if the charge density is rho, and here if I make a small d tau, a small volume here, then how much is charge in that d tau? It is the charge density into volume. So, rho d tau. So, rho d tau, that is the charge here, and similarly entire volume is now to be taken care of. So, in this whole volume we are taking small d tau, d tau, d tau, d tau, d tau everywhere, and then adding them together to give that capital Q. So, it is rho d tau integrated over the entire volume. This is this Q. So, minus ddt of this charge should be equal to integration of j dot dA, and this is that surface. This is to be integrated over the volume, and this is to be integrated over the surface, entire surface which is bounding this volume, the same volume and the corresponding surface of the volume. So, this is the relation. Okay, so now this is d tau here, volume integration, and this is dA here, surface integration. Now, if you remember, there is a beautiful relation called Gauss divergence theorem. We had talked at length in our part 1, where we discussed this Gauss's law. So, this is known as Gauss divergence theorem. And what does it tell? It tells that if you have some vector A, vector quantity A, which depends on space coordinates, which depends on x, y, z, it is not a constant vector. At different locations, the magnitude, the direction of this vector can be different. And then you have a surface, closed surface, some closed surface S, and on that surface you are integrating A dot dA. There is some vector A which depends on space points, we call it a vector field. So, this is a vector field, and then you have a closed surface, and on that closed surface you take those dA and then integrate A dot dA, A here, dA vector here, A here, dA here, A here, dA here. So, everywhere you calculate this A dot dA, add them. So, that is this integration. And on the other side you write it divergence of A. We give this symbol divergence of A, just say what it is, and then d tau volume. This is to be integrated over a volume, this is to be integrated over surface area enclosing that volume, and then here you have vector A itself, and this is divergence A, which is a scalar. So, if you multiply, if you take this divergence of A and then integrate over volume, and you take A itself and integrate over the surface of that volume, then these two are equal. This is known as Gauss divergence theorem. Okay. Now, what is this divergence? Once again we had talked about it. So, we had talked about it at length in our part 1, which we write like this, divergence of A is written like this. So, what is this quantity? What is this thing? So, just to remind you, if you have a point somewhere and at that point you want to calculate how much is this divergence of A. So, what you do is you enclose this point in a small surface, okay. You construct a small closed surface around this point where you want this divergence of A, and then you calculate this A and dot dA over this entire closed surface. The only difference here, this A dot dA, this A dot dA and this A dot dA, what is the difference? This A dot dA is over a much bigger closed surface, and this A dot dA is a small closed surface constructed by me around a point where I want this value of divergence of A, okay, and then divide it by the volume, by this whole volume, delta tau. I am writing delta tau, this is important now. I am writing delta tau to emphasize that this volume is small. And why small? Because I am going to take limit of this as delta tau tends to 0. This delta tau tends to 0, and therefore start with a small volume and take this limit. This quantity which is a scalar quantity, because A dot dA scalar dot product. So, this is a scalar quantity number, and everywhere A dot dA, you add number, you only get a number, scalar quantity, and therefore this whole thing is a scalar quantity, and that is known as divergence of A at that point. okay, at this point, at this particular point. So, divergence of A is another vector field. It can be different at different points. If I want the divergence at this point, I will construct a closed surface here, and then this limit may be something different, right. So, that is how this divergence of A is defined. But then if you are working in coordinates, if you are working with coordinates, so in some coordinate system, then there are expressions. There are expressions for this divergence. Every time you actually do not have to take limit and all that, and that expression I can just write from the book. Yeah. So, if you are using Cartesian coordinates, then this divergence of A is delta Ax delta x plus partial derivative this electromagnetism is a very nice topic to revise all your mathematics. Okay. So, delta A is written this way if you are using Cartesian coordinates, and if you are using cylindrical coordinates, then it is 1 over s del s and s a s plus 1 over s del phi, and then a phi and plus del az del z. If it is if you are using Cartesian coordinates, that means everything is a function of ax, ay, az. These are components, x, y, z components of A, right, x, y, z components of A, because you are using x, y, z Cartesian coordinates. But if you are using cylindrical coordinates, your coordinates are s, phi and z, and this A vector is to be decomposed in as, a phi and az. These are components of A in those directions s cap, phi cap, z cap. So, that is how it is written. And if you are using spherical polar coordinates r theta phi, then it is more longer expression 1 by r square del r of r square ar plus 1 by r sin theta del theta, and then sin theta a theta and plus 1 by r sin theta and del phi of a phi. I had talked a little bit about cylindrical coordinates in the previous lecture, but you have to be very conversant with these coordinate systems. So, you study these coordinate systems. It is given in the appendix in this book that we are using, and even otherwise you can find it is there. If you had done the course on electromagnetism part 1 electrostatics, then all those things were discussed in much greater detail. So, that is divergence. And coming back to this equation now, this is Gauss divergence theorem. Any vector field A dot dA integrated over the entire surface is same as this is integrated over the surface, and here it is integration over the volume, and integration of what? Divergence of this quantity. So, take the vector, integrate over surface, take the divergence and integrate over volume. These two are always equal. Use this thing here. So, this equation I am going to write once again. What is that? Minus d dt of rho d tau is equal to integration j dot dA. Look at this, integration A dot dA over a closed surface, integration J dot dA over the closed surface. This is the closed surface of this volume, and therefore this I can write as a volume integration. This was volume integration, this is also volume integration, divergence of J and then d tau, like this. So this you can now write minus integration V del rho del T d tau is equal to V here and then divergence of J and then d tau. And now you can the same volume here, the same volume here, d tau here, d tau here. So you can write this as, integration over V, if I take everything this side, minus del rho del T and what, minus divergence of J and d tau. You can put both pluses here or take this on the other side. So this equation is here, is equal to 0. And since it is true for any volume, we have started with any arbitrary volume and gotten all these things. So since this is true for any tau, this is true for any tau, whatever tau you want to take, you can take, and that will happen only if this del rho del T plus divergence of J is equal to 0. Now this is a point by point relation, no more integration, no more volume, no more surface. At a point, how much is this current density, volume current density? Of course the current density is to be taken in that neighborhood. At that particular point, how much is this divergence J, and at that particular point what is del rho dt at that particular time. So this is how this equation is known as equation of continuity, and we will talk more, or we will start our next lecture with this equation here.